So this video is part 2, covering the 12 core skills that you need for paper 1 for your chemistry exam. We've already covered how to use the periodic table, working out formula masses, working out individual formulas, and how to balance equations briefly. So we're now going to talk about some basics around mole calculations and different types of bonding. So first off, in this question, if an excess of sulfuric acid reacts with potassium hydroxide, so I'm going to start by writing an equation for this. So we've got sulfuric acid, H2SO4, plus potassium hydroxide. Reacts, we will form potassium sulfate. If you weren't sure how to work out the formula of potassium sulfate, go back to looking at this skill here. And because this is an acid and a base, we will form a salt, which is potassium sulfate, and water. In terms of balancing, to make this balance, we just need to put a 2 in front of the potassium hydroxide. The balancing is really important for the subsequent bit of this skill. So we are told that we have 168.3 grams of potassium hydroxide. And we've got to work out what mass of potassium sulfate is going to be produced. We're told that the sulfuric acid is in excess, so that means we don't need to worry about the details of this. So when we do mole calculations of this vein, you need to remember that there are 3 essential mole calculations equations. So the first is that number of moles is mass divided by molar mass. This can be used for solids, liquids and gases, and so is the most universal of the equations, and is also the first one we learn. It is also the one we need for this question. Not relevant to this question, but in other questions you should also know that number of moles can be equal to volume times concentration. So we use that in cases where we're dealing with solutions. And if we're dealing with gases, we can also use Avogadro's law, which is the number of moles is the volume of the gas produced in decimeters cubed divided by 24 decimeters cubed, because 1 mole of any gas will occupy that volume. So those are the 3 fundamental mole equations you should be aware of. So anytime you're doing a question with any of them, all you need to do is get used to writing down the 3 component parts of that equation. So in this particular case, we know that this is about mass. So this is the equation we need to use. So I'm going to start off by writing MRN underneath the potassium hydroxide. Now we're told the mass of that, which is 168.3. And we're ultimately being asked, what's the mass of potassium sulfate? So I'm going to do the same again, mass, molar mass, number of moles. Okay, so I'm going to use this equation in relation to these 2 things. Now, ultimately I've got to work out the mass here. Okay, in order to do that, I need to use this equation. So you can see here, there's a piece of information we haven't been given, and this is where we go back to this skill here. Okay, you have to be able to work out molar mass in order to work out the number of moles. So if you weren't aware of how to do this, you need to go back to this skill, but I'm going to recap it here as well. So for potassium hydroxide, okay, if we look on the periodic table, okay, potassium here has a molar mass of 39.1, and hydroxide is obviously 1 oxygen, which is 16, and 1 hydrogen, which is 1, so obviously that's 17. So the molar mass of potassium hydroxide is 56.1. I also have to be able to do the same with potassium sulfate. So again, potassium is 39.1, but I do have 2 of them this time. I have the sulfur, which is 32.1, which you obviously get off the periodic table, and then oxygen again, which is 16, but now we have 4 oxygen atoms. So the molar mass of potassium sulfate would be 174.3. So I've now got the molar mass. So now you can sort of see my route through this question. So I've been told the mass in the question, we've worked out the molar mass. So now I've got 2 out of these 3 things. So I can work out the number of moles here, and then I can use stoichiometry to determine the number of moles there and rearrange the equation to work out mass. So first off, if we work out the number of moles of potassium hydroxide we've got, it's 168.3 divided by 56.1, and that gives us a number of moles 3. Okay. Now the stoichiometric ratio here, if you look at the balanced equation, this is why balancing the equation was so important. Remember, balancing equations was this skill here. Okay, is that it's a 2-to-1 ratio. So you can see the 2 in front of the potassium hydroxide there. And so that means if I had 2 moles of potassium hydroxide, I would form 1 mole of potassium sulfate. I don't have 2 moles, I have 3. So since the ratio is 2 to 1, obviously that's the same as half. And so I have to halve 3, so my number of moles here is going to be 1.5. When I rearrange the equation to give me mass, it always ends up being the same thing. And so mass is going to be number of moles times molar mass. So I'm going to do, divide that by 2, just to give me the 1.5, just because that's what we've just done. And I times that by 1.5 by 174.3. And so we get a final mass of, this would be our answer in this particular case, 261.45 grams. So that would be like our final answer. So those kind of mole calculations are quite integrated, and it's important you practice that as a really integral skill. Obviously this video is intended as a summary of that skill and shows how it relates to the skills of working out formula mass and balancing equations, but it is important that you practice that on its own if you're not familiar or comfortable with the technique. Now this type of mole calculation, which follows on from this, is similar but different, and it makes use of an equation not mentioned here. So remember, these are our 3 mole equations. Number of moles is mass divided by molar mass, volume times concentration, and volume divided by 24 decimeters cubed. This question is how many oxygen atoms are there in 64 grams of oxygen? Now straight away, the moment you see mass, you should get excited, if that's the right word, because you know that this equation is the one that has mass in it. So most times this is the equation you use more than any other. If it's obviously starts talking about volumes and concentrations, get excited because you know it's this one, right? But this one, we've been given a mass. So anytime you see mass, there are only 2 equations in chemistry that you're likely to use when you have mass. One is this, and the other is the equation for specific heat capacity. And obviously that's not anywhere to be seen on here. So this is the equation that 9 times out of 10 we will use. So we've got 64 grams of oxygen. So you should understand there's one prerequisite bit of knowledge here, that oxygen, the formula of oxygen is O2. It's a diatomic molecule. Obviously it goes around as a covalent compound, which we will draw in a second. But holding that thought for a moment, because it's an oxygen molecule, the molar mass of the oxygen molecule, if you look in the periodic table, oxygen has the following information. So the molar mass of a single oxygen atom is 16. So an oxygen diatomic molecule, again, if you work out the relative formula mass, it's 16 times 2, and so the molar mass of oxygen is 32. So to work out the number of moles, we do mass divided by molar mass, and so we do 64 divided by 32, which is obviously 2. So that's the number of moles. Okay. Now the question here is how many atoms. Okay. So moles, remember, is a measure of the amount of substance. So the 4th mole equation that we use, these are the 3 main ones, but the 4th one we use is what I call the NR equation, which is a silly name, but it's because it's 3 N's, okay? N is the number of atoms or molecules. N is the number of moles, and Na is Avogadro's constant. So whenever you have a number of moles, like this one here, if you times it by Avogadro's constant, and Avogadro's constant you're told, which is 6.02 times 10 to the 23, okay, that's the number. If you multiply it by the number of moles, it'll tell you the number of molecules, okay? So we've got 2 moles of oxygen molecules here. That's very important. So I'm going to say that again. We've got 2 moles of oxygen molecules. So I'm going to do 2 times 6.02 times 10 to the 23. And just to show you that on the calculator, okay? So we do 6.02, we press 10 to the power times 10 to the power of x, or sometimes exp on your calculator, depending on your calculator, to the power of 23. And I'm going to times that by 2, which, as you can see, is 1.204 times 10 to the 24. Okay. Now, that is not my final answer here. There's one extra little trick in this question to be aware of. That is the total number of oxygen molecules in 2 moles. But each oxygen molecule, because it's diatomic, contains 2 atoms. So the final thing I need to do is I need to times this answer by 2, and that will give me 2.408 times 10 to the 24. That's my final answer for the exact number of atoms, because each molecule contains 2 atoms. Okay. So those 4 mole equations are the basis of all the mole calculations you need to deal with, and so you need to be confident with all 4. Obviously this summary only focuses on these 2, but equally you should be able to use this for titrations and this for calculating volumes of gas. So the next 2 skills that we're going to cover in this video are different types of dot and cross diagrams for bonding. So we have 2 examples here, one draw for oxygen and one draw for magnesium sulfide. So it's really important right to start with that you need to work out what type of bonding is going to be in each example. So you should recognise that magnesium is a metal and sulfide is a non-metal, and oxygen is just a non-metal. Okay, that's so important that you work that out first, because a metal and a non-metal is going to give me ionic bonding. So even though it's not written in the question, if I reword the question, it should say draw the dot and cross diagram for the ionic bonding in magnesium sulfide, but obviously it's assuming it's asking you to work that out. Non-metals will bond covalently. Okay, so remember, covalent bonding is a shared pair of electrons. Ionic bonding is when electrons are gained and lost and you form ions. So I'm going to do this one first, okay? So when the rules, remember, for ionic bonding, when you do the metal, so magnesium ordinarily has an electron configuration of 2, 8, 2, and so because it's in group 2, it will lose its outermost electron. So all metals lose their outer electrons, and so they're left with an inner shell which is full. So what we draw here is we draw the 8 electrons that are left over in the now full outer shell of magnesium after it's lost those 2 electrons. So because it's in group 2, we put plus, and whatever the group number of the metal is we put that there. Every single metal looks exactly like that, apart from you just change the charge number here to reflect the group. And obviously you don't write magnesium in the middle, you write the name of the metal. The only exception is lithium, because lithium only has 3 electrons to begin with, so when it loses its outer shell electron, it's only left with 2 electrons in its inner shell. So lithium would only have 2 crosses here. Every other metal looks like this. So that's an easy tip to do. Now when it comes to non-metals, okay, so in this case sulfur, because it's sulfide, what you have to do is look at the electron configuration. So for sulfur, it would be 2, 8, 6. Which obviously, just linking back, we worked out earlier, just as a reminder. And the sulfur, what you do is look at what group it's in. So it's in group 6, so you draw the circle, and whatever the group is, that's how many dots you do. So we draw 6 dots. We always have to make it up to 8, and so we make it up to 8 with crosses. So in this case, we're adding 2 crosses, okay? And then you put it in square brackets. Always the case. You put minus, because non-metals are always negative because they gain electrons, and however many crosses you've put, that's the number. So in this case, the number is the group number. In this case, the number is the number of crosses you've had to add to get up to 8. So you can use those rules for any metal or non-metal in ionic bonding. Now for covalent bonding, we have to just think again about the electron configuration. So for oxygen, it's got 8 electrons, so its electron configuration would be 2, 6. And it needs to, to get up to 8 electrons for a full outer shell, you've got to think it's got to gain 2 extra electrons. So what that means is it has to form 2 covalent bonds. Now oxygen, remember, is diatomic. So the formula of oxygen, which is obviously O2, means that the 2 oxygen atoms have to be directly bonding to each other. And because we know each has to have 2 covalent bonds, okay, they have to be directly to each other. So we draw that as a dot and a cross and a dot and a cross. We always show the covalent bond as a dot and a cross pair. Now that means that each of these now, if I just draw this a slightly different way, has a double bond. Okay, each one is because they're sharing electrons in that bond. Okay, but you have to make sure each individual circle adds up to 8. So we've currently got 1, 2, 3, 4 electrons on each of those oxygens. So I have to add 4 more on each, and now obviously you can go around each circle and count up how many red points there are, and obviously there are 8 on each one, so it meets the requirement of now having a full outer shell. So covalent bonding is a little bit more tricky, but you basically need to think about how many covalent bonds each type of atom can form and make sure that it does that, and you show the covalent bonding as a dot and a cross.